We're going to start talking about the open ocean, and Peter Landschützer is going to give us a first talk.
All right, thank you very much. So I've got the honor to start up this this series of talks now with the surface ocean, these observation-based estimates of the surface ocean, well, PCO2 gap-filled products and mapping products, and the resulting CO2 gas exchange estimates that we developed over the last years, and well, one of the reasons why we're here today. But it's actually quite nice timing that Rik was just talking before me, because in my next slide, please. I also wanted to first thank sort of the engine of the developments of the past year. So I would like to first say thank you to all, data science. One back, please. Yes. Thanks to all seagoing scientists, thanks to all data PIs, and thanks to all quality controllers for doing such an incredible job. Because really the reason why we're here and why we can start doing gap filling the way we do is because of the large abundance of observations. I mean, Rik mentioned it, that not the entire globe is filled, but it has been like a real strong increase in observations, and that's mainly due to the community effort of, I would say that in the establishment of basically the two largest service PCO2 databases, that's the LDO database and the SOCAT database. Because with sort of this increased abundance of observations, and over the last decades, we saw an increase from like globally about 6 million measurements in 2009 to now almost 25 million measurements. We now start daring, use statistical techniques, maybe based on neural networks or other interpolation techniques, and start filling those gaps, and not only fill those gaps in the time mean, but also start sort of expanding a bit, going a bit back in time to sort of reconstruct the ocean carbon cycle in the RC exchange over the past decades. Now, once you've used these smart techniques to fill these gaps, we usually just use some bulk formulation to calculate the RCCO2 flux. And on the next slide, I would like to show like some results from an effort that tried to sort of do an intercomparison of these first results that we received. So I think it was 4 or 5 years after sort of SOCAT was established, there were already 10 plus estimates. I think it were a total 14. Christian may be able to correct me there. That really started looking at the RC exchange on like multi-year to decadal timescales. So it was about the time to not only sort of analyze these, but also to sort of start intercomparing them. And these really ranged from these estimates that we had at the time really ranged from sort of really strongly model-related, model-based regression methods to sort of really sort of driver-based methods like these neural network methods, or linear regression or multilinear regression methods, to sort of methods that were completely independent from driver data, that just used sort of statistical methods to interpolate between the data. And what you see on the left-hand side of this slide on the bottom is one of the key figures, I think, from a paper by Christian Rodenbeck in 2015, who did this first in the comparison paper. And I mean, you can pick any point in time. So this is like sort of the annual RCCO2 fluxes. And you would see the difference of 1 petagram of carbon between these methods. And that's obviously due to data sparsity difference in the method used to interpolate the data. But there's also some striking things that you see there. And that is when you, for example, compare the decadal trends from the 90s and the 2000s, you see that despite these large disagreements at any given point in time, they very much agree on the temporal signal, at least on the longer term temporal signals. And this is something that I myself found very intriguing. And the very intriguing thing with this is that, particularly in the Southern Ocean, now moving to the right-hand side of this slide, that there's quite some agreement in the Southern Ocean where we actually lack essentially a lot of observations. So the observational cover in the Southern Ocean is sort of the least dense of the global ocean, I would say. But maybe the exception is the Southeast Pacific. But even there, you see that there's quite some agreement between these methods on decadal timescales. So now moving on to the next slide. So this was back then in 2015, but since then things have moved on a bit. So we've got sort of the development, we've seen the development over time from other groups. For example, we've got from two studies I would like to mention, the period in geoscientific model development, another two-step machine learning approach, or ensemble of machine learning techniques by Gregor et al. So we've seen like even more new sophisticated methods appearing, but we also see that now also seas like the Arctic Ocean or other marginal seas are now being mapped. So regions that have not been included in this 2015 intercomparison study, which would sort of make this ocean carbon sink estimate more complete. Also, we've seen implementation of these techniques to map the coastal ocean, for example, a study by Laure, which we hear more about later. But also we see like new data streams going into these estimates. So it's not, so we started with using the shipboard PCO2 observations, but now we've heard that there's other sensors out there like biogeochemical Argo floats from which we can sort of derive seawater PCO2 and include those in those estimates. So the next slide, please. And one development I also like very much to see, obviously for obvious reasons, because of also visibility, is that now also the global carbon budget uses, well, I would say visualizes some of these observation-based estimates in their annual budget. So I'm a bit lazy. I took an old figure, but so where you only see these green lines, where only 2 observation-based estimates are included. But last year they were already free in it. So I hope that at one point we get to the stage where we sort of have so much confidence in these observation-based estimates that we really say we totally derive the global carbon budget based on sea surface PCO2 measurements. And then my last slide. Yes, so I also wanted to mention sort of the key issues that we're still facing and why basically this working group exists. One of them is the area covered. So I've mentioned that sort of there's now new estimates emerging from Arctic Ocean and marginal seas, and they are not included. So I would like to see sort of these estimates grow together, because at the moment when we sort of compare integrated fluxes of different methods, so one covers about 88% of the ocean, the other one covers 92% of the ocean. So they're not really directly intercomparable because they don't cover the same ocean area. So there's coastal zones and marginal seas are partly excluded, and if they're included, they're constrained by open ocean observations and so not constrained by the fine grid scale that we actually would need. We're still wondering, I would say, what the contemporary and the anthropogenic carbon fluxes are. So, so can we really compare data-driven products with models at the moment when we know that they're not really illustrating the same quantity? We're still struggling with data sparsity, even despite this great community effort and all this great effort by the seagoing scientists. Regions like the Southern Ocean, it will take a while until new observations will come in. So at the moment, we're still struggling very much in these regions. And very important point also, we haven't fully quantified the uncertainties in this product. So we usually go back to known time series stations and known places where we have observations, but especially in these data sparse regions, we really need to have, get a good constraint on what the uncertainty of this product really is. And with that, I would like to pass on to my next speaker. Thank you very much.
Thank you. Thank you, Peter. Great. Were there any questions? We have just like 1 or 2 minutes. Any questions, clarifying points, particularly from the panelists is where we want to focus at this point. Okay. Let's see. If you do have any questions during the talk, particularly for the panelists, go ahead and put them in the chat is one way to make sure we see them. So, okay, great. Nikki Lovenduski will be next.
Hi, everyone. Good morning once again. My name is Nikki Lovenduski, and I was tasked to talk to you this morning about Hindcast models. Next slide, please. So what is a Hindcast model? Well, a Hindcast model is technically a hindcast simulation that has been conducted with an ocean model. So that is what is meant by that phrase as our working group has begun to use it. So I have a nice schematic here on the left of a typical Earth system model with its various components, a component for the atmosphere, the land, the sea ice, and the ocean. And in a Hindcast simulation of an ocean model, the only thing that's time evolving is the ocean component of the model. And for the purposes of our working group, the ocean component of the models that we're going to be thinking about also have active biogeochemical representation. So they are estimating, for example, air to sea carbon dioxide fluxes across the global ocean. A typical Hindcast simulation has the land component turned off, and also sometimes, but not always, has the sea ice component turned off. And it is forced with a data representation of the atmosphere. So it's not fully coupled to the atmosphere, but rather some data product is used to represent the atmosphere. And so typically some sort of reanalysis product is used. It's fed into the atmosphere as data, and the coupler sees it, and then the ocean component responds to that product. So you can think of, for example, the NCEP-NCAR reanalysis product. There are several reanalysis products that have been used for this purpose. So this sort of reanalysis product approach for a Hindcast simulation then will produce a quote unquote realistic spatial and temporal history of observed momentum fluxes and heat fluxes and freshwater fluxes that are then used to drive the ocean component of the model. And so what comes out then for the purposes of our working group is a quote unquote realistic time history of air to sea carbon fluxes, surface ocean PCO2, and other biogeochemical quantities that we might be interested in over some past historical period of time. Next slide, please. So there are essentially three flavors of Hindcast simulations that have been conducted with ocean models that contain ocean biogeochemical information and are currently available to our working group to analyze. And I've categorized them here in various colored bubbles. So on the left are the Hindcast simulations conducted with models that contributed to the global carbon budget. These models and the resulting air to sea CO2 fluxes are described in the paper by Friedlingstein et al. That Judith referred to in her introduction. It was published in Earth System Science Data last year. And they represent some past couple of decades up to the year 2018. Each one of these models, and I also want to apologize for the tremendous number of acronyms on this slide. There was no other way to do this besides to show all of them at once. Each one of these 9 models is forced with some sort of reanalysis product and produces a quote unquote realistic time history for those fluxes. On the right are 2 other bubbles, the green and the orange bubble, and these represent the IPCC class Earth system models that contributed to the OMIP project for CMIP-6. So to clarify, CMIP-6 is the 6th coupled model intercomparison project, and OMIP stands for the Ocean Model Intercomparison Project, which is its own sub-project under the CMIP-6 umbrella. If you'd like to learn more about the OMIP project, there are 2 papers that you should read. The first describes the physical protocol, and that is written by Steve Griffiths and co-authors, published in 2016. And the second describes the biogeochemical protocol, and that is in a paper by Jim Orr and co-authors in 2017. So OMIP 1 is slightly different from OMIP 2, simply because the reanalysis forcing product that's used to drive the ocean component of the models is different. So OMIP 1 uses the core reanalysis product, and it captures the years from 1948 to 2009, whereas OMIP 2 uses the Japanese reanalysis product, JRA55, also called JRA GOGO, and it captures the period from 1958 to 2018. I want to emphasize that there are many more modeling centers who contributed output so far to the OMIP 1 archive, and only 3 so far have contributed output to the OMIP 2 archive. I also want to emphasize that there's a ... at the bottom of each of these boxes, which suggests that there may be more model output coming online that captures air-sea CO2 flux history under both of these projects. This is the list as of, I'm pretty sure it was last week when I downloaded these output. Okay, next slide, please. So the purpose of this slide, or this figure, is to emphasize that the three flavors of Hindcast can actually produce different flavors of air-to-sea CO2 flux history. So here, what I've plotted is the globally integrated sea-to-air CO2 flux in petagrams of carbon per year. Negative numbers are into the ocean, from three simulations, all of them conducted with the same base model, which is the Community Earth System Model, or CESM. So the dashed dot line on top shows the resulting air-to-sea CO2 flux time history from the CESM ETH version, which was contributed to the global carbon budget. And then the two dashed and solid lines on the bottom show the time history of air-to-sea CO2 flux from CESM2, which was contributed to the OMIP project. So these output differ because in some cases the forcing used to drive the model differs. So for example, OMIP1 and OMIP2 are the same structural model, but the atmospheric reanalysis used to force the model is different. So you see, for example, in the 1970s, there's a very different estimate of the globally integrated carbon flux. But they also differ in terms of the structure. So the CESM ETH version of the model has a slightly different, it's very similar, but a slightly different structure than the CESM2. And then also the period of time for which the model is spun up before the experiments are conducted is quite different between these two sets of simulations. And then finally, there's an ever so slightly different boundary condition for atmospheric CO2 mixing ratio for the global carbon budget simulations than there is for the OMIP2 and OMIP1 simulations, and that's particularly relevant after the year 2015. Next slide, please. So if I put all of the available Hindcast model output together on one plot, and I don't make any sort of corrections for the area or the drift or anything at all, this is just raw output, globally integrated sea-to-air CO2 flux. The solid lines here are output from OMIP1, the dashed are OMIP2, and then the dotted are from the global carbon budget. You can see that there is quite a bit of covariance. The wiggles do match at some times, but there is also quite a bit of spread. So there is quite a bit of uncertainty in how the global ocean carbon sink has evolved. And that's something that I hope that our group can begin to discuss. Next slide, please. And then just to come back to what Peter showed a moment ago, or 8 minutes ago, I've now grayed out all the models and I've overlain the three observational products that were used in the last iteration of the global carbon project. And so what you can see here is that the variance captured by these observational products is different among the observational products. It's also different in some cases than the Hindcast simulations. And also there is a mean offset between the observational products, globally integrated carbon flux, and the Hindcast models. Next slide, please. And so typically what we have done is applied some sort of river correction to get the means into agreement with one another. And there's a little bit of debate about what that number should be. Should it be 0.45 petagrams of carbon per year? Should it be 0.78? Should we even be doing this, or is there another way forward? And I think that that's something that our working group will also discuss in the coming days. Next slide. I think that's the end. Yes, I do have Heather or May, whoever's running the slides, some backup slides for in case some issues come up during the discussion. You're welcome to show them. Otherwise, happy to take one or two questions and then we can move on.
Are there any questions for Nikki?
There's some questions.
Yeah, I had a question, Nikki.
Okay, go ahead and say it since we are.
All right. Yeah, I was wondering, this is Tim DeVries, sorry. I was wondering how the OMIP1 and OMIP2 forcings are different.
Yeah, so the OMIP1 is the core 2 forcing product. So, and it captures the periods 1958 to 2009. And the OMIP2 is the Japanese reanalysis that's used to force the model. So it's JRA GOGO or JRA 55, and it's time period. So it goes, it begins in 1958, 10 years later, and it extends through 2018. So it's it provides a time history up to more or less the present day. But they are different from one another in that reanalysis products differ from one another, right? What they ingest and how they back out the fluxes can be different.
How is,
Thanks, Nikki.
how is the atmosphere different? You also said the PCO2 in the atmosphere is different?
So the OMIP, it's the same PCO2 in the atmosphere. It's the OMIP PCO2 in the atmosphere, or rather the mixing ratio of CO2 in the atmosphere, Chi CO2, is different between the OMIP simulations and the global carbon budget ever so slightly. But that ever so slight difference can matter for ocean carbon uptake. And I hope that that's something that we can discuss as a working group.
Okay, thanks. We're going to move on to the next presentation. Laure Resplandy.
Yes, I'm gonna start with my video, but if it breaks up, I'll turn it off.
Okay.
Well, for including this, I'm happy to be part of that effort, and I'm going to talk today about the river loop and the natural ocean outgassing that is linked to it. Next slide. So one of the challenge that we have when thinking about the carbon cycle is to understand the partition between the land and the ocean, and that partition in the anthropogenic sink is key to understand the impacts like acidification in the ocean, but also the carbon climate feedbacks associated with the carbon cycle. Is the land sink going to be vulnerable in the future, or how is it going to how stable is it? What are the timescale on which it will store carbon? Next slide. And one of the challenge that we have is to constrain the natural flows that completely overwhelms in terms of magnitude those anthropogenic fluxes in the ocean, but also in the land. And in particular, that river loop, that I call that river loop, is the lateral transfer of carbon from the land to the ocean. And if it is not taken into account, it can be misattributed for an anthropogenic sink on the land because it appears as a drawdown and as a reduction, basically in the ocean. Next slide. Next slide. Yeah. So here I'm presenting some work on how can we find ways to constrain that ocean and river carbon flux. And what I'm presenting here is using a top-down constraint on the north-south asymmetry in those fluxes. And basically here I just split a very simple average global view, but split into south tropics and north. And some of the uncertainty that we have on the ocean and the river flux. So the river is mostly in the north and the tropics because that's where you have continents. And we have uncertainties with, for a long time, the ocean carbon community using more like 0.5 petagram of carbon per year transferred to the ocean by rivers. Where it has some, like in 2013, for example, there was some work that showed that it could be much larger than that, with large uncertainties, of course, and those were more bottom-up estimates. Both of them are based on bottom-up estimates of those river fluxes. Another thing that we have in that that would play out in that asymmetry between the fluxes between the north and the south is in the southern hemisphere, where you have a region of the Southern Ocean that takes up carbon and region that are a source of carbon. You have that compensation and the balance between those in-gassing and out-gassing fluxes is a question, with some of the mismatches between the different estimates being up to 1 petagram of carbon in that per year in that region. Next. And so what we've been using is can we use a metric that quantify that asymmetry specifically between the north and the south to to constrain it. And what I'm going to use here is the hemispheric asymmetry. It's basically that if you assume that it's a natural carbon flux, a natural current transport, it is balanced at steady state, and you would have the asymmetry between the north and the south, which is the average, this A, the average of the transport at 20 north and 20 south. Next. And this is what we published in 2018, where we used a series of models, 11 ocean and climate models that had carbon in them. And we showed that they have a strong relationship. They show a strong relationship between that asymmetry that I was talking about, that transport of carbon, and their transport of heat. And we see that in the Atlantic in observations. We don't have global estimates from observations, but we do see that strong link in the observation in the Atlantic Ocean. And the carbon is transported southward as the heat is transported northward, and that's because it's tied, the first order is tied to the meridional overturning circulation. And we do have constraints, several different constraints on the heat transport in the ocean, which is northward, and we know it's about 0.7 to 1.1 petawatt. And if we use the relationship displayed by those models, and that between heat and carbon and the observational range in heat, we can estimate that to be compatible with the heat transport, the southward carbon transport should be about 0.3 to 0.75 petawatt of carbon per year. Another thing that is notable here is that in that generation of models, which was the SEMI-5 generation, all are biased low in the heat, and obviously because it's tied to it, probably in the carbon transport. And that's because of the way they have their meridional returning. Specifically, the water masses that are formed they are usually too light and too warm, specifically the North Atlantic deep waters, for example. But we do have some constraint on the carbon transport. So now how can we use that? Next. How can we use that to, compare to the type of products that we have? And here I show some of the carbon transport. If you take those products that we have of PCO2 flux, correct them for anthropogenic carbon, here I use Katiwala, and you do see the carbon transport that would result from those products, going down in green from ocean inversion up to PCO2 based products in blue with two different river loop, a weak river loop of about half a petagram, and a stronger river loop here of 0.78 petagram of carbon per year. And you do see, and in gray, it's what you expect from the heat constraint, how much carbon transport you would expect. And you see that although the estimates agree within their large uncertainties, but they do show systematic differences in that north-south balance. And one thing is that the inversion tends to have a lower carbon transport, specifically those older model versions that are not ocean transporting, those are not observationally constrained, compared to the PCO2 fluxes, which have a larger hemispheric asymmetry. You also see that a stronger river loop improves the match to that heat constraint. And also a second thing is that a stronger transport to the south would implies that you have a stronger outgassing in the CO2, a stronger natural outgassing in the Southern Ocean that would offset partly the anthropogenic carbon uptake. Next, and so now I'm turning to other bottom-up estimates to try, because what I've showed here was mostly a top-down constraint on the transport, and maybe the river, some implication for the river transport. And this is some work that Seth Bushinsky did last year, where he, using Christian's and Pete's product, included the Takehome floats in the mapping products, the PCO2 based mapping product. And you see that including those new floats in the Southern Ocean, where you have not a lot of data in SOCAT, reduce the annual uptake by 0.4 petagram of carbon per year. There are issues with, it's not trivial to insert those floats in those mapping techniques, but it does go in that direction of actually having a stronger natural outgassing in the Southern Ocean which is compatible with our constraint. And I will finish next. Quickly, basically what I showed is a top-down heat constraint. The Jacobson number is a bottom-up estimate that had that land and inland waters bottom-up estimates at the time. And what I want to just introduce is with Pierre Régnier and Philippe C, we're working on an update of that bottom-up constraint that includes all the amazing progress that have been done in the meantime between estuaries and shelves. And could you skip 2 slides? And to my last slide, I mean, 1 slide, skip 1 slide. Another one. Okay. And no, just before. Basically, the idea is that in the older version of the bottom-up estimates, the coastal and the estuaries was very simple. And what was missing is the fact that those coastal vegetation in estuaries fix a lot of carbon. And basically, that reinforces the river carbon flux to the open ocean. And actually, I don't have time to go in detail here, but we're proposing an update on that is compatible with the top-down constraints. And my last slide, and I'll finish there. And the challenge ahead is how does that impact our ocean sink and our land sink partition? Thank you.
Thank you, Laure.
Yeah.
Do we have one question while we switch speakers?
I can answer. Tim DeVries asked me a question. I don't know if you want me to answer that.
Sure, I didn't see it. Yeah.
No, it wasn't a question. It was just a clarification. It's fine.
Well, it does implicitly. I don't agree with you because it does implicitly includes the river, because it does include the river transport.
Can you repeat the question, Laure, so everyone can understand what you're talking about?
Tim, as he said, the inverse calculation does not include the river carbon transport. It does implicitly because it takes ocean carbon data, and those include the carbon that was. So if you compute the carbon transport in the inversion product, you do actually include the carbon that was brought to the ocean by rivers and the outgassing linked to that carbon river flow. So that's what I mean by it includes it implicitly because it uses carbon data in the ocean interior.
That model, sorry, the model doesn't use carbon data in the inversion. I think the Gruber one does, but the other one doesn't. Yeah. But
okay, this is great.
Just a minor point.
Great fodder for conversation.
Yeah.
Let's go on to Tim's talk.
Oh, okay, Emma. Okay, yeah, so I'm going to talk about evidence from interior observations with talking about some of the inverse model estimates as well as some direct DIC-based estimates. Oh yeah, and thanks to Galen and everyone for putting this together. Next slide, please. Okay, so this was just a slide I put together mainly for myself to help myself think about the different processes that are affecting air sea fluxes in the ocean. Mainly I did this because the kind of different products that we're talking about and different estimates will essentially capture these different mechanisms to varying degrees. So some of them that I'll mention today basically only capture the anthropogenic CO2 part of this, so the emissions of CO2 and then invasion of that into the ocean, increase the DIC in the ocean. Whereas other estimates, like we think about the PCO2-based estimates that Peter Landschützer was talking about, those will take into account all the various different mechanisms that affect the ocean PCO2, including changes in biology, changes in the circulation and the freshwater fluxes, heat fluxes, etc. as well as we have this issue with the lateral boundary fluxes that is not necessarily taken into account. For example, in the ocean biogeochemical models, they typically don't have exchange with the lateral boundaries, not to mention the bottom boundary. So there's all these processes that work here. But a key conceptual distinction is between just that anthropogenic CO2 and then the remainder of the CO2 in the ocean, which is the quote unquote natural CO2. So yeah, next slide, please. So the ocean interior observations can basically help in two ways to think about these air sea fluxes. First way that I'll mention is that ocean tracer observations, for example, of CFCs or temperature salinity, radiocarbon, these kind of tracers, can basically be used to derive state estimates for ocean circulation. And then if we throw in the biological tracers, you can estimate state estimates for biology. And then these can be incorporated into models of air sea CO2 fluxes and kind of its indirect way to get at these air sea CO2 fluxes. Another way is using actual estimates of, actual measurements of DIC in the ocean. And then these can be used if we have sufficient estimates over time, can be used to basically see how the ocean DIC is changing over time. And then integrated globally, if we have kind of snapshots, we can say that the global change in inventory is equivalent to the global change in the air sea CO2 flux integrated. Next slide, please. So on the left is the kind of methodology for the inverse model approach. And then on the right is a methodology, a recent one, using the DIC-based reconstructions. And there's different ways to do both of these approaches. So I just picked two examples here. So on the left is the circulation inverse model that I work with. So this, in this case, ocean circulation model is fit to tracer observations, and DIC is not used in this model. And then that circulation is taken offline to simulate anthropogenic CO2 uptake. And then there's also a version, so that's the 2014 version. There's also a version where the circulation was fit to decadal data, so we get kind of a decadal average circulation, maybe. And then this can be used in the same way to estimate CO2 fluxes. On the right, this multilinear regression technique is basically used to apply to hydrographic data. So the DIC data are split into different time periods and then corrected for biological effects using the C-star tracer. And then the C-star data are mapped to a reference year. And then multilinear regressions are used to fill in the gaps in these reference year data sets. So this is similar to the approach taken by Chris Sabine et al. in 2004, kind of that first global map of the anthropogenic CO2 in the ocean, and then it's been extended recently by Nikki Gruber and coworkers in a paper in Science last year, where they looked at the difference in the anthropogenic CO2 in the ocean from 1994 to 2007 using this hydrographic data. I just pressed the forward arrow, but next slide, please. Yeah. So here's just some examples of like comparing some results from these. Top left, we have the MLR reconstruction of this anthropogenic CO2 column inventory change from 1994 to 2007 from Nikki Gruber's paper in Science last year. And then on the bottom there, this is just the anthropogenic CO2 column inventory in 1994 from the circulation inverse model. And these are totally independent. I think I can say that completely and totally independent methods for getting the anthropogenic CO2. So it's nice when they more or less agree. On the right, we have cross sections from in different basins of the anthropogenic CO2. From top row is the delta C star method from Chris Sabine et al. Middle row is another basically ocean inversion based on transit time distributions from Darren Waugh et al. And on the bottom is the ocean circulation inverse model. So again, all showing the anthropogenic CO2 in the ocean. Next slide, please. All right, so then this last one here, and this probably be the last slide I do here. This is showing a comparison of the ocean CO2 uptake from various different methods. So I guess I'll start with the ones that are kind of towards the bottom. So these are the quote unquote interior observation-based products. So the black and blue lines there are from the ocean circulation inverse model. Black is where we just use the anthropogenic, excuse me, the atmospheric PCO2 forcing only to drive the model, the air PCO2 fluxes. And then blue is if we allow some variability in the sea surface temperatures and also the piston velocities. This is just from reanalysis data, basically. And then the red is the EMLR anthropogenic CO2 reconstruction from Gruber et al. Based on the interior DIC. And again, these are totally independent. And we see that they're kind of, I guess, agreeing on kind of the outside of their kind of error bounds there. The error bounds on the OSIM, those are just kind of formal errors from like 10 different versions of the model, but obviously I think they're underestimates. They don't include some of the structural uncertainties. And then the top or upper lines there are air CO2 fluxes. These are the total CO2 flux, so not just anthropogenic, from the SOCOM compilation. And then, whoops, I have a misreference there. CSIR ML6, this is Greger et al. 2019, sorry. My Luke's messed up, I guess. And then the feed-forward neural network from Peter Landschützer et al. So clearly there's big spread here. So I just put on the bottom here things to note that we need to reconcile basically the mean ocean CO2 sink between the various methods. I think Laura was just talking about that with the river fluxes that are included in kind of the BCO2-based reconstructions, but not in the anthropogenic CO2 reconstructions. And then, so that's basically the non-ARC boundary fluxes. And also there's a difference there between natural and anthropogenic CO2. And then also looking at the differences in the variability, at least for those that resolve the variability over time, we need to resolve the, look at the mechanisms of this variability. And then also how much of the variability is real and how much is kind of just an artifact of the method. And I think Galen's group is working on some of that. So I think I'll just stop with that slide because I've probably did my time.
Okay, thank you, Tim. Do we have any quick questions? I don't see any in the chat. Okay, then we'll move on to the last talk of this section by Rik Wanninkhof, and then we'll have some time for discussion. Do we see Rik's slides, or there we are.
You can go to the next slide. This was my introduction slide. Okay. I am suffering from a slow internet connection, so I hope this will go okay. I'll change gears a little bit, and I think the take-home message is that the gas transfer velocity as a component of the gas flux is important. And I'll sort of put this, this adds a added uncertainty, and I think it's not necessarily a data gap, but it is an intellectual gap or a knowledge gap of how we deal with global CO2 fluxes. A lot of background information.
Yeah.
Hey, can you mute everybody except for Rik? Sam, I think we can hear you.
Okay, so thanks. So what I'll do in contact with a presentation by Andrew Watson at Ocean Science Meeting. It's a controversy which has been in the gas exchange community quite a while. Is, are we measuring the right delta PCO2? And this has a it has an important implication on our global estimates. Is that you see it in a small cartoon on the left-hand side, which is a preprint of the Watson et al. Results, where the top yellow line is the uptake if we're using a sort of conventional estimates of the delta PCO2. If we add a thermal component, you get the red line. And if you add a chemical and a thermal component, you get the blue line. And I've sort of put that in context on one of the older GCP graphs of ocean uptake, and that's the yellow line, which is sort of falling outside the uncertainty. And it is a difference currently if we apply these chemical and thermal gradients, it could be 1.2 petagrams. Next slide. Yeah, so just a bit of a primer to fluxes. We do not measure air directly in an operational mode. There are advanced CO2 measurements, which is basically measured in the air phase, looking at the variance of the vertical velocity and the concentration gradient. It is, it's method to understand the forcing of gas transfer and other applications. But what we are doing within this field of looking at global and regional air CO2 fluxes is we use a bulk formulation. And part of the confusion is that there are basically two ways to look at a bulk formulation. There is a physical and an operational definition. The physical definition is going to sort of old boundary layer theory, is that you basically have the flux, which is a product of a gas transfer velocity and a concentration difference over a molecular boundary layer at the top of the skin, sometimes called the skin layer. Where you need to know concentrations right at the and at the bottom of the diffusive boundary layer or mass boundary layer. The operational definition which we use is basically listed below, is where the flux is the basically the air-water concentration difference measured at a reference height. For air, it's commonly 10 meters. For water, it's 1 meter, and then multiplied by the solubility in the gas transfer velocity. Next slide. So good for this group is that we don't have to worry this right now, because there's a very capable group of experts who are addressing issues on uncertainty of gas transfer velocity. And this group, came together last fall. It was another OCB sponsored activity in Washington, DC, near Washington, DC last October, where basically this shop on ocean atmosphere interactions basically addressed some of the themes of a global program which has been around for a couple of decades, the Surface Ocean Lower Atmosphere Study, which has as themes which are directly relevant to the GAPS effort is greenhouse gases in the ocean, and an air, sea, and fluxes and mass energy themes, which are sort of important as we go. Specifically to the workshop, they basically delved down within the themes, and one of the workshop report chapters will be on air-sea gas exchange with David Ho from University of Hawaii as the lead of this effort. And one of the assessment and recommendation.
Rik, can you go back? We lost you for about 30 seconds there.
We basically, as part of this workshop, we have a workshop report with different chapters, and one of the chapters is going to be on air-sea gas exchange. I see I'm having still problems with connecting to the network. This has a section on biases in CO2 flux calculations, and we should pay very closely attention to the outcomes of this chapter. Slide. All right. Now, one of the reasons I think that sort of as a community, it's confused on where we sort of quite happily go from delta PCO2 to flux is if we look at sort of the global picture. Delta PCO2 has a huge influence on the flux, the direction, of course, but also the magnitude of the flux. And so these are two older pictures. These from Takahashi climatology. On the left is a delta PCO2. On the right is a flux. But we do have this gas transfer, sometimes called the kinetic forcing, which we parameterize with wind speed in order to go from one to the other. Next slide. Okay, I think the nice way to illustrate that that gas exchange does matter, and if we parameterize wind speed does matter, is if we do a small, simple thought experiment to say what would the air sea CO2 flux be if the wind was constant at the global about 7 meters per second over the ocean. In that case, you would get an uptake. This is an older estimate, but you get an uptake of 0.3 petagrams compared to a net uptake of 1.4 petagrams if you have variable winds. And one of the reasons is that if you look at a global ocean, it is the areas of outgassing, the tropical and equatorial upwelling areas commonly have low wind speeds, and then your uptake is in areas of high wind speed. So this asymmetry is quite important when you're trying to get to a net flux. Next slide. All right, one of the things is that we parameterize it with wind speed. We all recognize that it's not just wind speeds, it's the surface boundary turbulence, which is of importance. And one of the reasons that people who are looking at small scales and then apply it to large scales and small scales, you really need to look at these different mechanisms of transfer. And the question is, why can you go from a small scale approach where a lot of different factors are important to a very crude and simple global relationship, which seems to quote unquote work. And it's basically is that if you add these terms, you get something close to a quadratic relationship. And so the difference between using here, I just parameterize the terms as a polynomial compared to our conventional quadratic. Over the wind speed range of great interest in the ocean, the difference is very small. I think it's also worth remembering is if we look at the gas transfer, we have an uncertainty of plus or minus 20%, and these are optimistic estimates, and we have to keep this in mind when we are starting to look at global air sea CO2 fluxes. Next slide. Okay. So let's go into what's the fuss about. As I alluded to, is that if you want to balance the Earth radiation and water balance over the ocean, you need a cool and a salty skin. It's basically there's net evaporation of the ocean. The evaporation happens on the surface, and you net radiation, shortwave radiation at the surface, so that cools the surface. This is where the current controversy on air sea gas exchange and this is laid. And the reason is that, and Nikki referred to this as well, we want to get the global fluxes from a delta PCO2, the way we're doing it, it is critical to have a really accurate number. And if you have even small biases, that causes huge issues. And sort of this, back of the envelope calculation, a uncertainty or a bias of 1 microatmosphere in PCO2 is about 0.5 petagrams of carbon. think it's very important. The delta PCO2 over the ocean is relatively small, with a global mean of less than 8 microatmosphere. And then we have an added issue is that PCO2 is very temperature dependent. So these factors, basically, if you are looking at, looking at the boundary layer, the surface of the boundary layer is about 0.2 degrees colder, and it is saltier, which means it has a higher alkalinity. Let's go to the next slide. Okay, this is just sort of an illustration of sort of what the boundary layers are, and currently at higher level, if we don't just accept that we use an operational definition for delta PCO2, the issue is that you have a mass boundary layer which is embedded within a thermal boundary layer, and so a lot of discussion we're having right now is what is the relevant concentration gradient? Is it over the mass boundary layer or over the thermal boundary? Next slide. Okay, we can skip this. Is that basically we're working on sort of conceptual diagrams to see which one is the valid one. It is work in progress. I just want to assure everybody that a lot of us are thinking about this. Let's go to the next slide.
I have to cut you off soon, Rik.
Okay, and so it's basically. I think this is, basically my last relevant slide. There's one more to sort of show an implication, but it is what do we use for concentration gradient to get air CO2 flux? That is the big question. So the question is, what the appropriate concentration gradient? What is the CO2 at different locations in the boundary layer? The challenge is it's very difficult to determine this. And I think we have some approaches that we can use. One is the doing boundary layer modeling. And then global mass balance. And that's sort of the last slide, which I'd like to show. Okay, so essentially, I think this has a big issue. This is sort of one of our canonical figures of the sources and sinks. Currently, there is we believe there's a budget imbalance of 6%, which is within the uncertainty. Still, it is significant. If we had a higher uptake, this would change into a minus 6% budget. So it has a huge issue within global air CO2 fluxes. Thank you.
Thank you, Rik. And I'll just add to this. I think that really that 6 budget imbalance is sort of integrated over time, right? And it's sort of the standard deviation. If you look back. And so I think it would really imply a much smaller land sink here if the ocean sink was in fact larger. So I think that is a really important implication of any of these adjustments to a greater ocean sink. Okay, so we have, okay, so we just have a few more minutes here, 5 more minutes of discussion on the open ocean.
Yes, I've had some questions come in, so if you want me to read them off, I can.
Yeah, let me just, can I just take a second to summarize and make sure the panelists have a chance to
Sure.
Okay, so so I think Peter Landschützer gave a nice summary in his first talk. There are questions about the areas covered by our estimates, both from observationally-based products and from models, coastal zone and marginal seas, but even just the open ocean area is not always the same in these different approaches, and often the Southern Ocean is missing in some of the database products or some part of it, and so that needs to be accounted for. I'll just add that point. What is contemporary versus anthropogenic CO2 fluxes? I thought Tim's image was really useful to sort of make the case of there's a lot more included in this natural cycle, and often we're not clear maybe about what we're talking about, and we really need to be clear and figure out what we need to do to balance our understanding of the anthropogenic cycle versus the contemporary or natural. Questions of data sparsity and quantification of uncertainty. And then between Rik's talk about the delta, the PCO2 in the mean delta PCO2 being only about 8 microatmospheres, and what PCO2 are we noting? Are we really using to make these calculations? You know, we often in our models we use the global series of XCO2 multiplied by surface pressure as our boundary condition for our fluxes. And I also really would just like to add, you know, is that really appropriate when we're making these estimates, and how could we improve that that choice and how we make these estimates, both for models and products. So that was sort of my summary. Does anybody else on the panel have any burning questions or comments they'd like to make? Okay, seeing none. Heather, you had some questions that you got from the attendees.
Yes, so the first question we got in was for Peter, but others might want to jump in as well. Concerning the change in trend that the data show in the Southern Ocean, could this be due solely to changes in the distribution of the observations between the 90s and 2000s?
Yes, this is obviously a really good point, because like with most of the ocean, we've actually seen that like over the past years, we had like more increasing abundance of observations. And this is certainly something that many different groups have also looked at. It is on the one hand very difficult to go back in time to test, because you know, there's so little data. One thing that I can say about this, so in the end, my answer would be I cannot fully, with complete confidence, exclude that possibility. But something that sort of gives me confidence is this intercomparison project, that what I was showing as well, this SOCOM project, because there's different sort of methods that sort of there is this sort of the methods that treat the data differently. So some of them really just sort of do display interpolation, which would, in my view, or in general, be more sort of be more affected by data sparsity. Whereas sort of others that sort of use more the driving components from sort of predictor data that are sort of more abundant also in the past, for example, temperature and salinity, sort of might sort of have like less problems with that. And so you would expect, when you then do the comparison, and that would sort of really be one of the driver of this change, it would show up in this intercomparison. But it surprised me personally quite that it didn't. So yes, I cannot exclude the possibility that data sparsity is in part responsible for that. Then another point is what Galen showed in her introduction slide, is this sort of this test bed. Now we can use
or meeting followed by pound.
What is that?
Now we can use sort of model output to sort of really test it, because that one we have complete. So we have a complete time series, and we know what the truth looks like. We can subsample that and test it, and it really shows that some of the decadal variability that we see is indeed sort of is too much amplified by these methods, or at least one method that we could test so far. So yes, so it definitely shows. And when you include sort of synthetic float observation in this model framework, you see that this bias, this decadal bias, disappears. So as I said, I cannot fully answer the question, but there is some evidence that it does play a role. But on the other hand, it doesn't seem like all of it can be explained by the data sparsity.
Can I add to that quickly? So Peter, correct me if I'm wrong, but I remember you had done a sensitivity study where you excluded all of the Drake passage time series from SOM FFN.
That as well, yes.
Yeah, because there was some concern a couple years back that because that time series had begun to collect information in 2002, that could be influencing the swing. And in fact, if I remember correctly, it wasn't highly sensitive to the presence or absence of that the decadal variability seemed to still show up.
Exactly, yes. I mean, that go on now very much about the details there. I mean, we've done other tests where we just excluded chunks of 5 years of data. So we excluded like odd and even sort of 5-year periods, and then run the at least my method, the SRM-FN method, several times, and we couldn't find any clear evidence. But as I said, like this large test bed experiment does actually sort of suggest that there is something that might overestimate the decadal variability.
Okay, everybody, we've reached our time for this section, so we're going to take a 5-minute break and go start with the coastal ocean 5 minutes from now, and we will continue the discussion over the course of the day.